Everybody. Dr. Ripley here, and today we're going to talk about how we can move on from the z-test, which has the unrealistic assumption that we know somehow mysteriously, magically, the population standard deviation, to being able to use the sample standard deviation, which we do have. And our ability to do this is thanks to this gentleman, William Gossett, who in the early 1900s was working as the chief brewer and statistician at the Guinness Brewery in Ireland. So he was concerned with this very idea. How does the population distribution relate to a sample distribution? And he was so fascinated by this question that he spent the time that it took to randomly generate, using little scraps of paper that he wrote the numbers on, sample distributions from population distributions. And then he calculated those means and standard deviations and eventually produced enough of these distributions that he could use a mathematical equation to describe them. So we know that distribution as the student's t distribution. And we're going to use the t distribution to allow us to do statistical tests where we don't know population standard deviation, but we do have a standard deviation from our sample. All right. So the t distribution is different than the standard normal distribution that we've been using so far because it has more uncertainty. So if we look at this figure, you can see that our standard normal distribution here centered around 0, like we're used to seeing it, is its a nice normal tall shape. And this t distribution that's shown on here along with it is much shorter and wider. Excuse me. And its tails are going to go on a lot farther. And the reason for that is this additional uncertainty that we have, right? So the standard deviation of this t distribution, or the width of it, is going to be much wider than the normal distribution. All right, so it turns out that the t distribution not only doesn't just have a mean and standard deviation, it also has different shapes that are determined by the sample size. And instead of the sample size, you're actually going to use, like we do in the standard deviation calculation, this degrees of freedom. So remember, degrees of freedom is a term that we use for all of the independent pieces of information. And we're going to calculate it as little n, the sample size minus 1. All right, so, and we're going to abbreviate it little d, little f. So when we have a large number of degrees of freedom, the t distribution is going to look much more like the normal distribution. So larger sample sizes are going to give us a skinnier t distribution. And when we have a small degrees of freedom, we're going to have those more shorter, wider distributions. So depending on the sample size, for the same probability that we find in the tails, we're going to have different values of t. All right, so when we want to know a probability that's in the tail of our t distribution, we need to know the degrees of freedom. And so we're doing our hypothesis tests on a sample that we want to use to infer something about the population. So we're always going to have a sample size that we can, that has, that's that little n that we can use to find the degrees of freedom. So we'll find that eventually, if you have a big enough sample size, the t distribution actually sort of merges or becomes the same shape as the normal distribution. All right, so we're going to be using a t distribution table, and this is the very top of the t-distribution table that you have in your tables packet. And it shows a distribution at the top that looks quite a lot like the normal curve. And it's showing that there's an area C inside the middle of this distribution. And at the left-hand edge of this area, there is on the x-axis a value of minus t star. And on the right-hand edge of this area C, there is a value of little t star. All right, so just like the normal distribution, it is symmetrical. And like the normal distribution has values of little z along the x-axis, the t-distribution has values of little t. All right, so if we want to use the t-distribution, we're going to use, when we're doing inference with t-distribution, we're going to use by hand this table. So I want to orient you to this table. Notice that the top of the table says t-distribution critical values. So remember when we were doing confidence intervals, those critical values were the symmetrical left and right side values of z star that gave us a certain area in the middle. All right, so this table is really easy to use if we're doing confidence intervals, and we can do confidence intervals the same way we did with z star, just substituting t star instead. And for whatever confidence level we're interested in, say 95%, if we have a sample size of 7, that means our degrees of freedom is 6. Our T star, the plus and minus values that give us 95% of the area in the middle, that's going to be 2.447. All right, so the values in the table are values of T that are going along the x-axis. Right now, the distribution's symmetrical. So whether we have a positive T or a negative T, we're just going to use the table exactly the same way. And so it's kind of like you can just take the absolute value of your calculated value to use it in to use the table. Yeah, so this is the top of the distribution. That can help us find those values of T star. But how we're going to use it more commonly in class is if we scroll further down to the bottom, it's actually going to give us our P values corresponding with these particular values of T at the bottom. Notice that we have a one-sided value and we have a two-sided P value. So depending on our alternate hypothesis, we are going to use the one-sided if it's a one-tailed test, and we're going to use the two-sided if it's a two-tailed test. Now notice that the two-sided is exactly twice the one-sided. So you, the thinking scientist, don't actually need both of these. You just need to know which is which. Something else to notice is that this table starts to jump in numbers between, once it gets past 30, it goes by tens and then more. And then when we get up to 1,000, those numbers are almost the same as these values for Z star. All right, so when we have over 1,000 in our sample size, it actually comes out the same as the normal distribution. But I have never done an experiment with 1,000 individuals as part of the sample size. So it's not that practical. Okay. All right. So what we're going to do, suppose we have a experiment with 25 individuals in it. We are going to be able to say, okay, I calculated my value of T, so I'm going to use degrees of freedom 24. And suppose my value of T came out to be exactly 2.172, right? I would go down to the bottom, and if I had a two-tailed hypothesis test, I would say, oh, my p-value is 0.04. All right, so we're going to find our value of T in the appropriate row. And then we're going to go down to the bottom and it's going to tell us our p-value right there. All right, so it's a little easier to use than the standard normal table once you get used to it. And in the example problems, I show you how to use it for actual practice problems too. All right, so how are we going to do t-tests? Well, we're going to build on the z-test that we already know. So when we were learning inference, we were able to find a value of little z using the mean from our sample. The hypothesized value, the value we put into the null hypothesis, I think the true mean of this population is 27.3. Right, so that's that mu sub 0. We're going to find the test statistic z by using this equation. We had to use the population standard deviation because we had to make that assumption, right? And then we use the square root of the sample size here. And we would go to the standard normal distribution to find our p-value based on this value of little z. All right, so we're going to convert that exact test into doing a t-test simply by substituting little t for little z. And we can put the population, sorry, we can put the sample standard deviation S into that equation instead of the population standard deviation. All right, so this is great news. We have all of these values. All right, so we're going to have a single specified value that we want to compare. We're going to say, I think the true mean of my population is this. And we're going to find our test statistic by comparing our X bar to that specified value. Then finish calculating this t, and then we're going to use the t-distribution table or software to find the p-value, just like I showed you from the table, also using the degrees of freedom. Okay, so we didn't have to use the degrees of freedom for our standard normal. That's a new thing with our t-distribution. All right, so it turns out that this test, we're going to have some more interesting tests we can do using t. I suppose we could use them with z, but nobody ever does. So if we're only comparing our sample value to one single specific value, we aren't really doing an experiment. We're estimating a parameter, more or less. So we want to do things that are more interesting. All right, so this slide has a lot on it. We'll spend a little while on it. There's 3 types of tests that we can do using the t-distribution. And the one that we have done so far, the same as with the z, is actually something we're going to call a one sample t-test. And that means we have, so these cylinders are representing our samples, the things we actually have in our hand. And these clouds are representing the population. So somewhere out in the real true population, it has mean mu and standard deviation sigma. And we have taken this sample from the population to try and estimate this mu, compare, or say we think this mu is a certain value. Okay, so for the one sample test, that's going to be just like the scenario of the z-test or the one sample t-test. We're going to have a set specific value that we want to compare our sample mean to. All right, and we're using the sample mean as evidence of whether this set value is actually what our true mean is, right? So in order to do a manipulative experiment where we say, I want to see if there's an effect of something on the variable I'm measuring, we need to do some kind of intervention. All right, so I'm indicating an intervention or a treatment with the yellow star. So we have 2 different ways that we can implement a treatment. We can have 2 completely separate groups of individuals. We took a sample and we did nothing to them, and we took a different group of individuals and we applied a treatment to them. Now we did everything else about how we kept the individuals in our control in our treatment. We kept every single other thing about them as exactly perfectly the same as we possibly could. So the only difference between them is going to be this treatment. We want to know the effect of fertilizer on plant growth. We want to know the effect of radiation on bacterial mortality. We want to know the effect of some factor, right? Some explanatory factor on some kind of variable that we're going to measure. And these are all going to be quantitative variables. All right, so what we're asking in this experiment is, are the control and the treatment, did they act like they came from a single population with mean mu, that the mu of the control and the mu of the population the treatment came from? Are they the same or do they differ, right? So our null hypothesis is going to be that they came from the same population, that their means are equal to one another. And the alternate is going to be that they actually act like they came from different populations, right? And so if that's true, then we would say that this treatment had an effect, in fact, a statistically significant effect. All right, in our paired or one dependent sample experiments, it's very similar to the two independent samples in the idea of what we're doing, except instead of having completely separate individuals in the control and the treatment, we have one set of individuals, right? One sample, right? And we're going to impose the treatment on them, and we're going to have some kind of measurement from before that treatment versus after that treatment. So basically, we're going to take two measurements on the same individuals. It's the easiest way to think of this experimental design. There's other ways that we can have not a before and after scenario, but we can have related samples. We can have people who lived in the same household versus, and we want to see the effect of something that happened maybe after they left that household. So nature versus nurture experiments do a lot of these paired designs. So there's pros and cons doing these two different ways. You only need half as many individuals to do an experiment like this. And when we have a lot of variation between individuals, we actually may get a better reading of the impact of our treatment if we look at this before versus after. If we have lots of individuals with lots of variation that are in the control and lots of individuals, different individuals with lots of variation in the treatment, it may be harder to see the effect, right? Because we'll have bigger standard deviations. All right, so we call this the paired um, experimental design because we're going to have a pair of measurements and they have to be associated with one another. We don't separate them and calculate means on them separately, right? We have to keep those two pieces of information together. All right, so sometimes this is called dependent samples. Sometimes it's called sometimes it's called a one sample. I prefer to call it paired because then you don't get confused with the one sample, one sample. Sometimes people call it two dependent samples. So I'm going to stick with paired for this experimental design. All right, so same thing. Your null hypothesis is that the before and the after, the true mean of them is the same, that this intervention, this treatment had no effect, versus the alternate hypothesis that they're acting as if the befores came from a different population than the afters, in which case we'd have a statistically significant difference. All right. So we already did the equations to find the test statistic for the one sample. Let's look at what they are for the paired t-test and for the two independent samples t-test. All right, I've got paired on the left here, and then two independent samples on the right. All right, so let's just go back to our equation for the one sample t-test. So notice it's got x bar minus mu sub 0 here. And then we've got the s over root n. In the paired, we're basically going to hypothesize that the difference between the two means, we're going to do this in both the paired and the two sample. We're basically going to have to subtract the before minus the mu after. We're going to subtract the mu1 in the two independent samples from the mu2, and our null hypothesis is going to be that difference is 0. All right, so we don't have to know mu0 because our hypothesis is that it's 0. So it just disappears from this equation. Right, so that's the other way we got around needing to have some piece of information that we don't actually know. It's really genius, right? So we don't see a mu0 showing up in either our equation for the paired test or for the equation for the two independent samples test, right? So for the summary, the paired test has two related, dependent, or non-independent samples, or one sample that we measure twice, right? We have the same individuals or the related individuals that we're going to measure. And we have two ways to write our null hypothesis. Either the true mean of the difference between the before and the after is 0, or we can write it as mu after equals mu before. And we're going to do a lot of examples using this before and after because I think it's the simplest way to think about how these experiments work. All right. So what we need to calculate in order to evaluate this hypothesis that the mu diff equals 0, we need to actually find the mean of the differences between our two measurements on the same individual. And I'm going to work an example of this for you where you'll see how it works. So make sure and look at the video with the example problems before you start working on any homework or worksheets. So we'll calculate the differences between the befores and afters. We'll take the mean of the differences. We'll find the standard deviation of the differences, and then we'll plug that in with the sample size. So little n, we only have one little n because we have one set of individuals we took two measurements on. Right, so that one's pretty easy to calculate. Now for the two independent samples, we have two distinct unrelated groups of individuals. One group is exposed to a treatment and the other isn't. All right, our mu sub or our null hypothesis is that the true mean of one of the groups is equal to the true mean of the other group. Right now, our alternate hypotheses are going to depend on whether it's one-tailed or two-tailed. So I didn't write these down on this slide. So if it's a two-tailed test, it would be mu1 does not equal mu2. So one-tailed test, we would have a alternate hypothesis with a greater than if we expected mu1 to be bigger. We'd have a less than if we expected mu2 to be bigger. All right, so what do we need to do to evaluate our hypothesis? We need to find a value of our test statistic. We're going to take one mean and subtract the other. So we'll need to calculate a mean and a standard deviation of each of our, for our control and for our treatment group. And we'll have a sample size for each of our groups, the control and the treatment. They don't have to be the same. Experiment works better if they are. Now, we have to combine together or pool together the variances and the sample sizes between the two different groups. This is a simple calculation formula that I'm going to give you to use by hand. There's a more complicated version of how to more accurately pool the variances. We're going to let Excel do that for us. All right. So this isn't the very best formula to use. We're only going to use it for hand calculations just because it's relatively relatively simple. And when you're doing any real kind of actual, you know, uh, experiments for publication, you're going to use software. You aren't going to use any kind of hand approximations for your real work. All right, so the t-test, just like the z-test, are based on assumption that they fit to our model distribution. So our data actually need to be normally distributed for these t-tests to work well. Okay, now if the sample size is larger, they don't have to be as perfectly normally distributed. And they're actually pretty robust to um, deviations from normality, right? So we're going to have this assumption for our t-test that when we're getting ready to do a t-test, we have to check these assumptions to make sure our data, the test is going to be valid for our data, all right? So we're going to make a histogram of our data to check if they're normally distributed. However, even if they're not very normally distributed, we can still use these tests, and that's going to depend on the sample size, right? So for the one sample in the paired t-test, if our little n is greater than 15, it doesn't matter that much if the data is normally distributed. They're going to be close enough to normally distributed. The t-test will work well. All right, so larger sample sizes are better. For our two independent samples t-test, it works best. The sample sizes in the two samples are approximately equal, and that they're both greater than 5. And so it's very hard to get an experiment. I mean, I wouldn't want to do an experiment where I had that few individuals anyway. So our two independent samples t-test, it's pretty hard to find a scenario where we've actually done a meaningful experiment and we can't use it. But we are going to talk more later about what to do in case we find that the assumptions for our t-tests are not met, right? We'll have different tests we can do in that case. All right, so when we have the two independent samples, they can have different standard deviations because we have those two different samples. So the assumption for the two independent samples t-test only, because it's the only situation that this applies to, is that the standard deviations are close to equal, approximately equal. All right. And we're gonna make a eyeball kind of approximate evaluation of if they are close enough. And this is very easy to evaluate. It's almost harder to explain than it is to look at in practice. All right, so suppose we have two samples and one of them has a standard deviation of 5 and the other one has a standard deviation of 7. All right, so the larger standard deviation is no more than twice the size of the smaller one. All right, so we have the larger one is 7, smaller one is 5. If we take 5 and we multiply it times 2, we get 10. All right, so between 5 and 10 is the range where we can have our other standard deviation and they're close enough that we can do this test. All right, when we have Excel doing this test for us, it is actually going to do a statistical test and test if the standard deviations are equal. And if they aren't, it's going to do an adjustment on the data for us, right? So we don't need to worry about this if we're using Excel. All right. So those are the assumptions that need to be met for our t-test. And when we learn the tests that we can use if these assumptions aren't met, we'll talk a little bit more about evaluating these assumptions. In the meantime, we're going to practice doing t-tests. And if I say this is a homework assignment problem, do a t-test on it, you're going to assume that the data is appropriate for that kind of test and proceed. All right, make sure and watch that example problems video up next.